Hi viewers, in this class we are discussing traffic signal design. Suppose there is an intersection which has four legs, 1, 2, 3, 4, four legs, and suppose I am considering this leg. Suppose there is a divider here and we have two legs. And suppose there is a traffic signal which shows we have three signals, right? Red, amber and green. Say red, amber and green. We have three indications. Suppose there is a red signal for this approach, so all the vehicles will be waiting in queue like this. All the vehicles will be waiting in queue. Once the red signal becomes green, what will happen? The first vehicle will move. You have to start and accelerate. The vehicle should get acceleration, and that acceleration will take some time. The first vehicle, you see, first vehicle, it will take some time to leave this signal area. What happened to the second vehicle? This time will get reduced. So the starting time to clear this area for the next vehicle will come down. The time has been reduced. It got reduced. And similarly for the third vehicle and fourth vehicle, and then it reaches smooth movement of all the vehicles, right? A smooth curve like this, and whatever the time last here, whatever the time last here, even the signal is green, whatever the time last here for starting and accelerating of the vehicles, the first few vehicles, that time is called startup lost time. Startup lost time. Got it? We have startup lost time, this time. And then after green we have amber, right? You call it yellow color also. What happens once the vehicles are moving? After green, whenever amber is there, the vehicles which have crossed this line will be clearing from here, and the vehicles approaching here who has seen that signal will be stopping. So we can't leave this area, so better we decelerate and stop it here, stop the vehicle here. Means even if we have time, even if the signal is allowing, we are decelerating the vehicles and stopping the vehicles here. Means that is also last time, called clearance last time. Startup last time and clearance time. This combination of these two is called last time. We have last time. And now we have red time, green time, and after green time we have amber time. So combination of these three. So red time plus after red we get green time plus amber time. So sum of these three is called cycle length. Length means time, it is time only. Cycle, we call it cycle length. Is it clear up to now? Then we will move on to the further topics in this traffic signal design. So for finding this cycle length, according to Webster method, we have cycle length as 1.5 plus 5 divided by 1 minus y. I'll tell you what are all these things. I'll tell you and explain you these things. So according to Webster method, cycle length C is equal to 1.5 into last time, total last time. Right? Total last time. If there is an intersection, and suppose we have only straight movements, only through traffic is there. Suppose through traffic is there, so we can do like this. For phase 1, we allow these two, and again in phase 2 we allow this through traffic. It is a possible case, right? Then what we do is, we have two phases, so number of phases is 2. And last time, total last time is given by NL plus R, where N is number of phases, and L is last time per phase. What is last time? Just now we have discussed. Last time is combination of startup last time plus clearance time. For this phase, suppose we are calculating for phase 1, last time for this phase. And what is R? R is called all red time. Means for all the traffic, the entire signal is red. Means pedestrian traffic. So pedestrians will be moving all along the roads. So all red time means red for all the approaches. We can call it pedestrian crossing time. Generally pedestrian crossing time is all red time. And now TL is clear. And what is Y? Y is sum of small y and I. I is the phase. I is the phase number. First phase, second phase, third phase. I is the phase, and Y is ratio of flow of that phase to the saturation flow. What is flow? We know traffic volume. That is flow. U is traffic volume. You can also call it as flow. Flow of the traffic approaching a signal. That is flow. And this is also not just flow, it is critical flow. What is critical flow? Suppose we are at phase 1. So these vehicles are moving. So this suppose this traffic is some 500 vehicles per hour, say PCU per hour, and this traffic is say 400 PCU per hour. So what we got is this traffic is 500 and this traffic is 400 PCU per hour. What is critical flow is highest of these two, higher of these two, or even we have different approaches, highest of them is called critical flow. Means if 500 vehicles can pass through this phase, less than 500 vehicles will also pass the signal. So that is critical flow for that phase. And saturation flow means maximum number of vehicles that can flow. We have capacity, right? Maximum flow that can pass through the signal if the entire signal is green. So there is no red. The maximum number of vehicles that can pass through is the saturation. And Y, for this particular case, Y is Y1 plus Y2. That is Q1 by S1 plus Q2 by S2. So Q1, Q2 depending on the traffic, S1 and S2 depends on the width of the road. So as the width increases, saturation flow will also increase. So as for IRC, it is for 3 meter, it is 1850, for 3.5 meter, 1890, like that it goes on. If the width of the road is more than 5.5 meter, so per ECU per hour per lane. Now we are clear. The next part is green time. Now effective green time GI is equal to QI by sigma QI into cycle length minus total lost time, and small qi is the critical flow of that phase and sigma qi is the sum of all critical flows. Now actual green time or the display green time which we see on the traffic signal is effective green time minus amber time plus lost time for that phase. Now we will see a few examples to get better understanding in this topic. So there is an intersection which has through traffic only. So the data is given as 400 PCU per hour per lane, similarly 600 here, 300 here and 200 PCU per hour per lane. And saturation flow is given for this approach as 1800 and for this approach as 1200. Lost time, that is lost time per phase is given as 2 seconds and all red time is given as 8 seconds. Find cycle time and green times for a two-phase signal. For a two-phase, what we do is so phase 1, let us take this, and phase 2 take this. So we have 400 here, 600 PCU per hour per lane. Similarly, 300, 200. So critical flow for this phase is 600, that is higher of these two. Similarly, higher of these two is 300 PCU per hour per lane. Saturation is also given, S1 as 1800 and S2 as 1200. Last time is given 2 seconds. We will calculate total last time as NL plus R. Number of phases is 2. Last time is 2 seconds and red time is 8, which gives us 12 seconds. And now we will find out C. We know 1.5 total last time plus 5 by 1 minus y. For this we need y is equal to y1 plus y2, that is q1 by s1 plus q2 by s2, which comes as 0.33 plus 0.33 plus 0.25, which comes as 0.58. Now you calculate C. 1.5 into 12 plus 5 by 1 minus 0.58, which comes as C, comes as 55.2 seconds. 55.2 seconds. And now we'll calculate green times. Effective green time for phase 1 is, we know, Q1 by sigma Q into C minus total last time. If you calculate this, it comes as 28.94 seconds. Similarly, calculate G2. You calculate this. And now if you want actual green time, so amber time is not given, so effective green time minus last time, that is 2 seconds, is the actual green time. Now last example we will see in traffic signal design. We will design a 4-phase signal. The data is given like this: 4-legged intersection, and 4-phase signal. So the data is given like this. So there is free left and we have straight and right movements, and the data is given in PCU per hour per lane. So we have these movements. $370, $180, $290, $210, $290, $240, $220, and $130. Something like this. We have to do is first find critical flows. So suppose we will take phase 1 as 1, 2, 3, 4. Phase 1 is this and Q1 is 370. Higher of these two. Similarly phase 2, phase 3, phase 4. Phase 2 we have 290. Similarly phase 3 also 290. Phase 4 is 220. And the data given, I'll write it here. Saturation headway is 2 seconds. Last time per cycle, last time per phase, that is per cycle also 3 seconds. All red time is 20 seconds and amber time is 3 seconds. So saturation headway for all the approaches is given as 2 seconds. You know, if you know saturation headway, we know from the traffic engineering first part that saturation headway, if you have given saturation headway, then 3600 divided by saturation headway will give you saturation flow, that is 1800 ECU per hour per lane. Now calculating last time, that is NL plus R. Number of phase is 4, last time per phase is 3, plus all red time is 20, which comes to 32 seconds. Similarly, C naught, you know the formula, 1.5 into total last time plus 5 divided by 1 minus y, and y you calculate here. Y is equal to sigma of Qi by Sy, that is 370. Saturation flow is same for all the approaches, therefore 370 plus 290 plus 290 plus 220 divided by 1800. You get y as 0.65. So now if you substitute y here, you get C as 151.428 seconds. So we take it as 152 seconds and calculate. So cycle length minus total last time, we get 120 seconds. And we know effective green time is Q1 by sigma Q into C naught minus last time. So sigma Q we have 1170, which gives us 370 by 1170 into 32, okay, 120, which comes as 37.94. We take it as 38 seconds. If you calculate the remaining also, you get green time for second 30 seconds, for third phase is 30 seconds, fourth phase 22 seconds. Got it? And now we will draw cycle times, means red, amber and green for this example, which comes as, I forgot to explain you one thing. In this present case, we are considering amber time as 3 seconds, and also last time is 3 seconds as in the data. So as we know, actual green time is equal to effective green time minus amber time plus last time for each phase. Now in this case, as the amber time and last time are 3 seconds, so they gets cancelled, and actual green time is equal to effective green time. And as we draw these things, the figure looks like this one. That's it, and all the best.